Alrighty. The last little section in Chapter 2 is about molar mass and the mole. We're going to do some simple, quick calculations with molar mass. If you've had any chemistry before, like you were supposed to for this class, you've at least seen or encountered the mole, hopefully. The nice thing about the mole is it's just a definition, it's just a conversion factor, and if you're well practiced at setting up conversion problems for the units to cancel, the mole and Avogadro's number is just yet another one of the conversions that you can use in a calculation. So treat it just like any other conversion, getting the units to cancel after we know what its definition is. So I've seen many times that the mole is referred to as the chemist's dozen, where a dozen is just a group of objects, happens to be 12 objects in a dozen, but that are grouped together to make them easier to count or easier to handle. Right? Eggs are sold by the dozen because it's just a nice convenient package of 12 eggs, and then you can count out however many dozens you need just by counting out packages. And a pair, very similar. A pair is a grouping of 2 objects, just like a dozen is a grouping of 12 objects, and a mole is a grouping of 6.022 times 10 to the 23rd objects. That is referred to as Avogadro's number, and the official unit, I suppose, for Avogadro's number would be particles per mole. And all that means is that there are 6.022 times 10 to the 23rd particles per 1 mole of something. We could write that exact same thing for a dozen. We could say 12 particles per dozen, or 2 particles per pair, or Avogadro's number of particles per mole. Okay? So with that definition down, all we need to do is set up conversion factors so that units cancel. So get out your calculator. Get out your calculator, or come and borrow one. Let's do this first one together right here. If I have 1.38 moles of aluminum, and I want to know how many aluminum atoms that is, the first thing that we need to know is that whenever we say moles of a substance, that means we're counting whatever kind of particles that substance is made of, right? So aluminum is an element, right? Elements are made of atoms. We'll talk in probably in the next chapter how we do that with compounds, whether it's molecules or formula units that we use. But elements are, of course, made of individual atoms. So 1.38 moles of aluminum, we'll set up this conversion factor like that. Oops. And where should I put Avogadro's number in this fraction here? On the bottom? Read this carefully. Which one of these are the particles here? The aluminum atoms or the moles of aluminum? The atoms are the particles. Okay? So let's say that's the particles we're talking about in this case. Okay? A particle is anything, any little individual thing, but in this case, aluminum, its particles are atoms. So Avogadro's number goes here. I'm just going to write E23. Okay. So there are 6.022 times 10 to the 23 aluminum atoms per what? Per 1 mole of aluminum. Okay. So all that tells you is you need to multiply. Moles of aluminum cancels. 3 significant figures, right? This version of Avogadro's number has 4 significant figures to it, so that could limit your answer if you've got other things with more sig figs to them. Okay? There are versions of Avogadro's number with up to like 6 sig figs or something like that. I think that's as far as it goes now. Okay. But in either case, here's what'll limit us. So what'd you get for an answer, rounded? Times 10 to the what? 23rd? 23rd what? Aluminum atoms. Okay. Let's get in the habit, starting now, whenever we're dealing with some sort of chemical substance in a calculation, every time for our unit to be a measurement unit as well as a substance. Okay? That's going to come in very helpful to us when we're doing reactions, when the substance is changing. Okay? So that's why I said moles of aluminum and aluminum atoms. Okay? So why don't you set up this one right here. Start with 9.23 times 10 to the 25 lead atoms. Okay. Why don't you set that up and see if you get an answer? Make sure in the conversion factor that Avogadro's number is next to the particles. In this case, our particles are lead atoms. Good. Right. Lead atoms into moles of lead. So, which unit of this fraction will have Avogadro's number? Yep, it'll be Avogadro's number of the atoms per how many of the moles? Per 1 mole. Okay. And I think 3 sig figs again. So what'd you get with 3 significant figures? 153 moles. Okay. If you haven't yet, I want each of you to make sure that you can punch that in. If you did 9.23 times 10 to the 25 divided by 6.022 times 10 to the 23, and if you got anything other than 153, come and see me. That means you're entering things a little funky into your calculator. Maybe come and talk to me afterwards, but make sure that your calculator gives you that answer. You can always avoid any possible issues with scientific on the bottom of a fraction by using EXP on your calculator. That keeps the power of 10 right with the number. Okay? You can get into a little trouble if you're actually doing times and 10 and a caret, where sometimes that can get separated from the number, especially if it's on the bottom. But if you got 153, you're doing great. Okay? So using Avogadro's number, I guess, is interesting because it's just some big group of atoms, but it only actually becomes useful when we can relate it to something that we can measure, because we can't measure number of atoms. We don't have a molometer that we can count out individual atoms. So what we use is the relationship between mass and moles. And that's where all this stuff comes from. You may recall that the atomic mass of carbon-12 was 12 AMU exactly. Okay? The atomic mass unit was the unit that we used to talk about how massive an atom is. Okay? And by definition, carbon-12 was 12 AMU. Well, it turns out by definition, the molar mass of carbon is also 12 with the unit of grams per mole. Okay? The reason that Well, the reason that AMUs are what they are is because we relate that exact thing with grams per mole. Okay? And that comes back to why Avogadro's number is a particular value. I like to draw a little picture here. So draw a little ball there. That's a carbon-12 atom. Right? Its mass is 12 AMU. Okay? Carbon-12 atom. How about that? I like to shade spheres a little bit so it's not just like a circle. Okay? So then, draw a little plate, make a nice pile of carbon here. Okay. Let's say this is 12.01 grams of carbon. And 12 grams, well, not 12.01, I'm getting ahead of myself. Let's say 12 grams carbon, okay, of carbon-12. Well, let's stick with this one. Okay? How many atoms are in that pile? One mole. 6.022 E23 atoms. Okay? That's why Avogadro's number is the value that it is. Okay? It's to get us from this number in AMU, from a single atom, into this number of grams. Okay? Avogadro's number is how many atoms it takes to get AMU of one atom into grams, okay, of a whole pile of atoms. So Avogadro's number is a constant then, because different atoms will have larger AMUs to them, okay? But a constant Avogadro's number will give us that same number of grams. Okay? So take a look. Let's compare with just natural carbon, 12.01 AMU. Why is this value a little bit larger than that one? What does natural carbon have to it that carbon-12 doesn't? Isotopes. Has 3 isotopes. Carbon-12, carbon-13, and carbon-14. So this is that natural mixture of the 3 isotopes. That's why on average it's just a little bit over 12. It's 12.01. Okay? So a mole of carbon, because it'll contain some of those heavier isotopes, will be a little bit more than 12 grams. It'll be 12.01 grams. Okay? Neon, 20.18 AMU, 20.18 grams per mole. Okay? If we start with a larger atom, we're going to end up with a larger pile of atoms, but still Avogadro's number. Right? So be sure to have some kind of picture in your head about what Avogadro's number means. Okay? And what its significance is. Okay? It's really it's kind of arbitrary, because going from AMU to just gram, a particular unit, but that's what was originally decided on, and that's why Avogadro's number is what it is. Okay? It's how you take any atom from its AMUs to grams of that atom. Okay? So let's do a quick calculation here. 12.5 grams of silicon, and I want to know how many moles of silicon that is. Where am I going to get the molar mass of silicon in order to fill out this relationship? Off the periodic table, absolutely. There's one on the front cover of your notes, always. There's one that I can pull up at any time. Okay. Atomic number is on top. That's just number of protons. But the weighted average atomic mass is down below it. And, as we will now pretty much completely be calling it, that's the molar mass, because that's how many grams there are per mole of something, okay, of that particular element. Okay? So I see 28.09 there on the periodic table. Where will 28.09 go? next to the, yeah, 28.09. Okay? What you need to know is that molar mass is grams per mole. Okay? Molar mass, grams per mole. Okay? So, comes from the periodic table for elements, at least. Okay? But the number on the periodic table, that's how many grams there are per mole. Okay? So 0.445, is that what you got? Okay. Try it going the other way with 2.6 moles of silver. Calculate for me how many grams that would be. Look on the front cover of your notes if you need to. What is silver's molar mass? 107.87. Grams or moles? That's how many grams there are per 1 mole. Okay? So what's the answer to this one? Yep. Two significant figures. Here's a trailing 0 with no decimal point. 280 dot would be wrong. That's 3 sig figs. So a better way would be like what I heard right here, 2.8 times 10 to the 2. Okay. Best to avoid insignificant trailing zeros. Okay. 280 isn't wrong because we would assume 280 had 2 sig figs. The problem is we don't quite know about that trailing 0 with no decimal point. So we would assume 2 sig figs with that. But still, you're better to avoid trailing zeros that are not sig figs. It's best to avoid those by putting it in scientific notation if you need to. Now, before you turn the page, what if this question up here asked how many atoms of silicon, or a lot of times that's called silicon atoms. If I wanted to do silicon atoms, you already wrote it, but I can just include right here. What would we do? Yep, because they're Avogadro's number of silicon atoms per 1 mole of silicon. Okay. A general rule, and you can get an answer or whatever, that's fine. A general rule, a nice thing for you to look at, is that if you're ever asked how many atoms are in something, if your question is how many atoms, your answer will almost always be a huge number of atoms. Okay? Why would it make less sense for your answer to be something times 10 to the negative 18 atoms? You can't have, well, and that would be a fraction of an atom. Okay? So yes, it's true, you cannot have negative grams of things, you cannot have negative atoms, okay? But even if your answer is positive times 10 to the negative something, that would be one small fraction of an atom. Okay? an answer in atoms is never going to be less than 1 atom. Okay, so think about that. That should make some sense to you, but you would be surprised at how many answers I see that are given in tiny, tiny fractions of an atom. Usually it's because Avogadro's number was placed on the wrong side of a fraction. Okay, but that's a really easy thing to check for. If your answer is in atoms, you should be having a lot of atoms. Any reasonable sample of anything is going to contain a lot of atoms. Right? So you guys get that. All right. So what I want us to try to do here is a somewhat complicated multiple step word problem. Okay? We like to do that in chemistry. What I'm interested in, and I don't know, there was probably somebody that really needed to know this at some point, but let's say we have a cube of aluminum, 3.51 millimeter sides. I've given you the density, and I want to know how many atoms of aluminum that is. Well, several ways to tackle this. I like drawing pictures, even though I'm terrible at it. I think it's good for the thought process whenever you can sort of start to visualize something. But especially when we start talking cubes. So, drawing pictures is helpful. Making road maps is helpful because that's a length. Okay. So, and if we're just doing atoms is our answer. Okay. Atoms of aluminum. What is the only unit that can get us into atoms? What is the only relationship that we've had with atoms in a conversion? Yeah, grams don't go right into atoms, okay? But moles do. Okay? We can use Avogadro's number, right? There is Avogadro's number. Okay. And then, what was the other unit that got us into moles? Just on the last page. Okay, we can get into grams. Okay. Oh, and look at this. Here, in my problem, I've got a relationship between grams and centimeters cubed. Okay. So a lot of it's going to have to do with what gets done right there, because I gave you the length of one side in millimeters. We ultimately need a volume in centimeters cubed. So think about that for a second. If you have an idea about how to go from that one to the next one, see if your neighbor might think you're on to something. There are a couple ways you could go with that, so I'm curious to see what you come up with. So, what do you think? So what'd you do? You cubed it? Oh yeah, there you go. I like that. So here, if you're stuck, I'll give you a couple other little things, right? The volume of a cube is just the length of one side cubed, right? How many millimeters are in a centimeter? They're just 1 × 10 apart. So like I said, there are a couple of ways you could go. You could go millimeters to centimeters, and then do this to get the cubic unit. You could go millimeters and cube it first, and then do centimeters that way. Both of them have things you need to be slightly careful about. So there's a little hint. Pick one way, though. Doesn't matter. If you do that first one that I have there, the volume is length cubed. Okay? If you do that first, let's see here. No, that works. That's just fine. You can do them in either order. There is in other words, when you go from the straight unit to the cube unit, that's a discontinuity. That's sort of a break in your linear pathway. So don't forget about that. Don't forget about that. But so what'd you do? Yep, you converted to centimeters and then cubed it and then went from there. Yep, that works. So what'd you do? Careful there. Since 1 millimeter is 10 centimeters, 1 millimeter cubed would be 10 cubed centimeters cubed. How did you do that? You cubed it. Yep. Yo. Mm-hmm. Mm-hmm.
Cube root of both of them in order to figure out one side.
If you were given the volume in millimeters cubed, yep, you could do the cube root to get the length of one side. Yep. Mm-hmm. Yep, that's the inverse of what you did there. Okay. How are we doing over in this corner? What are we thinking here? Okay. Millimeters cubed. Yep. Then millimeters cubed to centimeters cubed. Okay. I think that's looking pretty good so far. What are you thinking over here? Yeah. So I think you can't really have this fraction right here. So maybe just get an answer right here, and then you need to cube it in order to get a cube. Yeah. Okay. How are we doing over here? Be a little bit careful because while there is 1 centimeter in 10 millimeters, when you cube those, you also have to cube those numbers. So I think you need a 10 cubed right there. Yeah. Okay. How did we do over here? Centimeters. Yep. You actually don't need to write down the answer for all these intermediates like that. What you can do, if you've got just a string like that, you can just put all those fractions right next to each other and punch it all in your calculator at once. Okay. That's pretty good so far. I think you better do 10 cubed there. Because you cubed that and you cubed that, so you better cube that. Yep. And then for this one, check out right there. Okay? So here, let me write one of these ways, at least. What we could do, one way of doing it, at least one pathway here, is starting with that length and just cubing it to get cubic units that we were given, right? If we did that, we get cubic millimeters. Okay. Make sure that it would pretty much be written like this, and you could type that out and get an answer, or you could just put it in your calculation like that. That would work just fine, as long as you remember when you're multiplying it in to distribute. Right? You'd have to do 3.51 cubed in there. Now, well, it's true, like we said up above, that 1 centimeter has 10 millimeters. Okay? It's not quite true that 1 cubic centimeter is 10 cubic millimeters. What do I actually have to do right here? Yep. When we take a linear conversion, right, just a length conversion like this, to one that has units raised to a power, the most common error I see is forgetting about that or using an incorrect power or something like that. So that would get us to centimeters cubed, which we could go to grams, then we could go to moles, then we could go to atoms. Okay. So where does this conversion come from? Right here. Density. 2.70 grams per cubic centimeter. Okay. Right there. Where does this conversion come from? Molar mass? What is the molar mass of aluminum? Okay. And then where does this conversion come from? Avogadro's number. Okay. So that's one setup. Before I write the answer down, let me show you the other way of doing this. We could have taken 3.51 millimeters and just done a linear conversion, right? The issue is you sort of need to get an answer here, right? You need to get 0.351 centimeters, which then you need to cube. So we kind of have to stop there and say that the volume is 351 centimeters and cube that whole thing. And then you can continue on, right? Because that gives you centimeters cubed at that point, and you can continue on from there. Okay. That's the only difference. Okay. So anybody get an answer? I agree with the 2.6 at least. Yeah. Might have been rounded a little bit differently because I got 2.61. So I need to double check your rounding. What power of 10 then? Yeah, I got 10 to the 21.
Wouldn't it be
Where would the 2 come from? Oh, yep. 2.70 is 3 significant figures. Yep. When a decimal point is shown, trailing zeros are significant. Okay. All right. So that's what I got, at least. No entire guarantees that that's correct, but if you got a different power of 10 from that, it probably came from here, or if you constantly find yourself being off by 1 power of 10, it usually means you're entering Avogadro's number wrong. Okay? If you use the E or EE key, don't type 10. Okay? I've seen that mistake an awful lot. That E already has a 10 in it. Okay? Be careful with order of operations, especially if you're dividing by things. Make sure that stays together on the bottom of a fraction if it needs to. So, okay. So that was just one example of a sort of combination problem. But this kind of roadmap here, where we've got particles to moles here. Atoms are the particles with elements, at least. To grams. Okay. Avogadro's number there. Molar mass there. That is a common scheme that you should get used to going back and forth with. We're going to get more practice of that on that later on in chapter 3 when we do stoichiometry, calculating reaction amounts and so on. Okay. So, did anybody else have any questions about this? This is so silly, but it always sticks with me. One of my students gave me a big poster that I think she had drawn at some point, but it had a picture of Particle Park. Yeah, well, she called it the Mole Hill and the Graham Canyon. So it had pictures. It had Particle Park and a Mole Hill and the Graham Canyon. I don't know. It's a high school thing, I think, but it always makes me chuckle a little bit. So.